Welcome to Math with Professor V. This is video lecture for section 5.2 on relative extrema for business calculus. So remember, in the last lesson, we looked at finding critical numbers for a function and determining intervals where it's increasing and decreasing. Now we're going to build on that idea and find relative maxima and minima. But first, let's establish a definition. What is a relative min or max? So let C be a number in the domain of a function f. Then f of c is a relative or local maximum for f if there exists an open interval a to b containing c such that f of x is less than or equal to f of c for all x in the interval from a to b. You're probably reading that definition thinking, what the heck does that even mean? I'll draw a picture and help you out, and it should make a little bit more sense. So on some interval from a to b, we have this x value, c. It has to be in the domain of f. And then maybe the easier way to read this inequality is that f of c is greater than or equal to f of x. So the function value, f of c, let's say it's right here, it's greater than or equal to all the function values on that interval from a to b. And then when you're looking at this, probably you go, oh yeah, that makes sense. That's a local max. Some books use the word local, other books use the word relative. Okay, same thing. And then similarly, our definition for a relative or local min is that there's some open interval, again, a to b, containing c such that f of x is greater than or equal to f of c for all x in that interval. So again, if you want to read it that f of c is less than or equal to f of x, that might be helpful. C's on this interval. Say this is f of c. And now f of c is smaller than or equal to all the function values on that interval. Oh yeah, that looks like a local min. Okay. And then we say a function has a relative or local extremum, the plural for which is extrema, at c if it has either a relative maximum or a relative minimum there. So maximum, minimum, extremum, those are singular. Maxima, minima, extrema, those are the plural. All right. One other thing to make note of is that if c is an endpoint of the domain of f, then we only consider x's in the half open interval that's in the domain. Now let's just make sure we're pretty good at visually identifying from a graph where a function has a relative max and relative min. So here's just some arbitrary function. Don't worry about what its equation would be. Could we, just by looking, identify where it has any relative minima? Yeah, just look for like the smallest function values within an interval. Looks like there's one here and one here as well. So how would we report or write our final answer? Well, I would say there's a relative min at x equals -7 and at x equals -2. I'm identifying where they're at. Sometimes though, most of the time, you're asked for the actual min value. In that case, they want the function value. So you want to give the y value. The relative min value is the function value. So it would be f of -7, which is, if you come over here, 1, 2, 3, 4, 5, 6, 7. Yes, I counted correctly. It's -2. That's the y value. So f of -7 is -2. And we had one more, f of -2, which is also -2. So this is really the best and most complete way to write your answer, because when you're asked for the relative min or max value, we want the function value, and then I'm also able to identify where they occur since we're using function notation so nicely. Okay, are there any relative maxima here? Yes, I see right up there. That looks like a max. Perfect. So the relative max occurs at x equals -4, but if we want the actual value, relative max value, then we give the function value. So then we should write f of -4, which is, looks like +3. Good? Okay, so you can see how function notation is very useful for these kinds of scenarios. It succinctly gives so much information. Now, what if we don't have a graph? How are we able to determine where these maxima and minima are occurring? Well, thankfully we have calculus. And in the last lesson, we learned how to find critical numbers and identify where a function is increasing and decreasing. And that's precisely what we need in order to determine where a function has a relative max or min. So here's the first derivative test. Let C be a critical number for a function f. Suppose that f is continuous on a to b and differentiable on a to b except possibly at c, and that c is the only critical number for f on that interval from a to b. Then we say f of c is a relative maximum of f if the derivative f prime is positive from a to c and then negative from c to b. Don't worry, you're not going to have to memorize this statement. You're going to do the first derivative test by drawing that same number line that we learned how to make in that last lesson. So you put f prime, and then remember we got really good at testing where it was positive and negative to figure out where the function's increasing and decreasing. You're doing the exact same thing. So c is some number, critical number, on the interval from a to b. So c is in between here. And all this is saying is f prime is positive from a to c on the first interval, and then negative from c to b on the second interval. So if the function goes from positive, increasing function, if the derivative goes from positive to negative, then the function goes from increasing to decreasing, which means, hopefully you can see just by these arrows, that our function has a relative max at x equals c. Very good. And f of c is that max value. Similarly, f of c is a relative minimum of f if the derivative is negative from a to c and then positive from c to b. So let's draw again. So here's f prime. We have some interval from a to b, and there's a critical number between. It's negative on that first interval, the derivative is. So that means the function's decreasing. And then it's positive on the second interval. So then that means the function's increasing. And hopefully by drawing these arrows, it's clear to you, yes, there's a relative or local min at c. Now, if you do this number line test, that's going to give you all the information that you need. And on occasion, you know what happens? There is no sign change in the derivative. So you might have a to b, here's c, and it stays negative on both sides. And c is a critical number. But if the function is decreasing on both sides, or if it stays increasing on both sides, then it's not a min or a max. It's just nothing. It's just a critical number, and that's all that we can say about it. Okay, so there needs to be a sign change in the derivative on either side of the critical number in order for it to be a relative min or max. Good? Okay, perfect. So now let's put this to use and practice some examples here. Find the x value of all the points where the functions defined as followed have any relative extrema, and then find the values of any extrema. So when they say find the values, they want the y values, they want the function values, okay? And then make sure you write the domain for each of the functions before you get started, because remember, if we have any domain restrictions, those can't be critical numbers and they can't be relative mins or maxes. So we have to be aware. Don't worry though, the first example starts off nice and relaxing. It's just a polynomial. We know those are pretty harmless. Their domain is all real numbers. Okay, so to begin the problem, we want to identify where the critical numbers are, which means I have to take the derivative. So g prime of x is 3x squared plus 6x minus 24. And then our critical numbers come from where the derivative is 0 or where the derivative does not exist. Now this is a polynomial. I'm not going to get any from where it doesn't exist. That's not going to happen. But certainly we can see where this derivative is going to be 0. So 3x squared plus 6x minus 24, let's set that equal to 0. You can factor out a 3, or I'm just going to divide everybody by 3, so I don't even have to look at it anymore. So divide by 3, divide by 3. Then this is x squared plus 2x minus 8 equals 0. So it's looking like this will factor, right? And we can find the critical numbers pretty easily. This will factor into x plus 4 times x minus 2 is 0. And so we end up with x equals negative 4 and x equals positive 2. Good. So those are my only two critical numbers. Now I'm going to make my number line just like I did in the last lesson when we were finding intervals of increase and decrease, and put them on the number line, -4 and 2. And so now I want to test and figure out whether the derivative is positive or negative in each of these three intervals here. So say we pick something smaller than -4, like -5. You can plug it in to this version of the derivative or to the factored one here. All I did was divide by 3. That's not going to change the sign of the derivative. But be careful whenever you manipulate it to solve for the zeros, okay? So let's see. If I put -5 in, this factor's negative, this factor's negative. So two negatives being multiplied together make it positive. So the function's increasing. Will you forgive me? This is G prime, not F prime. Oh my goodness. The math police are coming for me. Okay, from -4 to 2, oh, zero's in that interval. Let's test with 0. If I plug it in here, it's going to be negative. Derivative's negative. That means the function's decreasing. And then something bigger than 2. How about 100? Or 3. Positive, positive. The derivative's positive. Function is increasing. Okay, very good. So it looks like right here at x equals -4, we have a relative max. If you just look at the arrows, right? Increasing, decreasing, it looks like there's a little max right there. And then at x equals 2, we've got a relative min. And then the problem asked for the actual values, the actual function values. So you're going to go ahead carefully plug in -4 for x into the original, and 2. So I did that for you already just so we can get the ball rolling. So g of -4 is 82. That's our relative max. And then g of 2 is -26. That's the relative min. Okay, how was that one? Good? Boom, there we go. Lovely. Let's move on. Let's do another example. We're not going to work with polynomials all the time. So here we have f of x equals 3 times x to the 5/3 minus 15 times x to the 2/3. Now, remember, we got to identify the domain. It might be a little tricky when it's written in this form with rational exponents. So if you want to remind yourself, this is the same thing as 3 times the cube root of x to the 5th. This denominator is the index on the radical. Minus 15 times the cube root of x squared. And what do I know about cube roots? Anytime this index is an odd number, we don't have any restrictions because you can take the cube root of a negative number or 0 or positive. So the domain is, again, all real numbers, which is nice. If you want a shortcut way of doing it, you just look. If these are odd, then you're going to be good to go. No restrictions. Okay. But let's use the way f of x was written here to find the derivative. It'll be much easier. So f prime of x, I can just apply the power rule. So leave that constant 3 alone. Bring the exponent 5/3 down in the front. And then subtract 1, that's the new exponent. So 5/3 minus 1, or minus 3/3, is 2/3. And then moving on to the next term, minus 15, just the constants come along for the ride. Bring the exponent down front, subtract 1, 2/3 minus 3/3 is -1/3. Did you get it? Okay, let's clean up a wee bit more. So notice, these 3's cancel. This is just 5x to the 2/3 minus 15 times 2/3 is 10. And then I'm going to put x to the -1/3 in the denominator. So I'm going to write this as 10 over x to the 1/3. And remember, the easiest way to identify critical values is when your derivative is written as one expression. I don't want two terms like this. I'm not happy about this. So I want to get a common denominator. Remember, this 5x to the 2/3 is just over 1. So my common denominator is going to be x to the 1/3. I'm going to multiply that on the top and bottom since 5x to the 2/3 is missing that. And then this is going to be just fabulous. Watch this. So we've got x to the 1/3 in the denominator. When I multiply x to the 1/3 and 5x to the 2/3, I add these exponents together. 1/3 plus 2/3, that's 3/3, so x to the first. So we have 5x to the first minus 10. Boom! Isn't that beautiful? There's f prime of x. Yes. So now let's find our critical numbers. They come from two places, where f prime of x is 0 and where f prime of x doesn't exist. And then hopefully you remember I told you guys about a little shortcut in the last lesson. When you take the time to write your derivative as one term and you have one fraction, if you want to find where it's 0, you're just going to look at where the numerator is 0. So you're just going to set 5x minus 10 equal to 0, which means x is equal to 2. And then if you want to find where the derivative doesn't exist, then you just set the denominator equal to 0. So you would set x to the 1/3 equal to 0, x equals 0. You're not allowed to do that though if you didn't take the time to write it as one expression, one fraction. Okay, so here's my two critical numbers. Let's put them on our number line. 2 and 0, that's all we got. And then this is f prime. So let's pick a number smaller than 0. How about -1? Don't pick anything too wild. 5 times -1 minus 10, that's negative. -1 to the 1/3, that's just taking the cube root. It's going to stay negative. So negative divided by negative, positive. And then put an arrow going up to show that means the function's increasing. Between 0 and 2, say we pick +1. 5 times 1 minus 10, negative. Positive. Negative divided by positive is negative. Function is decreasing. And then bigger than 2, 3, 4, 8, whatever. Let's do 8 because it has a nice cube root. 5 times 8 minus 10, positive. Cube root of 8 is 2, positive. So positive, the function's increasing. Good? Okay, so just by looking, I can see, okay, at 0, we've got a relative max. And we want the function value. So f of 0, that's just going to be 0. And then we have a relative min. Can you see? At f of 2. Very good. F of 2, relative min. Now this one's not coming out so nice. So 3 times 2 to the 5/3 minus 15 times 2 to the 2/3. This is kind of nasty. If you want to clean it up and write an exact answer, I'll show you what to do, but probably you won't have to do that in your class. You could just punch that in your calculator and give a decimal so that you would know how to graph it, because that's where this is all going in just a moment. Not today, but soon. But if you really die hard and you want to simplify it, 2 to the 5/3, I could write that as 2 to the 3/3 times 2 to the 2/3, right? Those add up to 5/3. Minus 15 times 2 to the 2/3. This is just 2 to the first. 2 times 3 is 6. So this is 6 times 2 to the 2/3 minus 15 times 2 to the 2/3. And then you can just, these are like radicals. So 6 minus 15, yep, that's -9 times 2 to the 2/3. And then 2 to the 2/3 is cube root of 2 squared. So -9 times cube root of 2 squared is 4. But I doubt your teacher's going to need that. Should you want to impress them, though, there you have it. And then in your calculator, this is about -14.3. Okay? So there's the relative min. Good. Just check with them how they always want the final answer. All right, let's look at another kind of function. I thought I was going to need more space, but I didn't. So here we go. F of x is x squared minus 6x plus 9 divided by x plus 2. So this time for the rational function, we do have a restriction in the domain. Remember, we don't want the denominator to ever equal 0. So the domain is all x's such that x is not equal to -2. We're going to have to keep that in mind throughout the problem. Do you guys remember, in a rational function, when the denominator is 0, once it's fully simplified, meaning nothing's canceling, we don't have any holes, that tells me that we have actually a vertical asymptote at x equals -2. Okay, so let's be mindful. All right, let's proceed and take the derivative, f prime of x. So we're going to do the quotient rule. I'm going to recite the little rhyme. So we've got low d high, so denominator times derivative of the numerator, which is 2x minus 6, minus high d low, so that's x squared minus 6x plus 9. D low is just 1, over low low, x plus 2 squared. Now, you could start multiplying everything out if you want, or you could factor further. What do I mean by factoring further? Yeah. So I have x plus 2 times 2x minus 6 is actually 2 times x minus 3 minus, and then x squared minus 6x plus 9 factors into x minus 3 squared, or x minus 3 times x minus 3 over x plus 2 squared. This is exciting because look, I can take out an x minus 3 now from everybody. Ooh. And then what am I left with? Well, I have 2 times x plus 2, so that's 2x plus 4, minus x minus 3 over x plus 2 squared. And then this leaves me with x minus 3 times, when this negative distributes, that's going to be negative x plus 3. So 2x minus x is x, and then 4 plus 3 is 7 over x plus 2 squared. Beautiful. Okay, so now we can easily identify our critical numbers. The derivative is 0 when, just look at the numerator, when is it 0? We factored it, so it should be easy to tell. At x equals 3 and at x equals negative 7. And then when does the derivative not exist? Well, just look at when does the denominator equal 0. That's at x equals negative 2. But that's not a critical number. Oh, look, I got too excited. I already wrote does not equal. At x equals negative 2, that's not going to give us a critical number because negative 2 is not an element of the domain. When you write this symbol, it means, and you slash it out like that, that means it does not belong to. It's not an element of the domain, as we've reminded ourselves here. So negative 2, nope, not a critical number. But I do need to put it on the number line. If you'll remember from the last lesson, we did one where it came up. So here's f prime. I'm going to put a little dashed vertical line to remind me that at negative 2, we've got a vertical asymptote. And then put the other critical numbers in their appropriate places, negative 7 and 3. Okay, and then let's pick something to test this interval, like x equals negative 8 would be good. I don't even have to look at the denominator, because see how this is squared? Everything that I plug in is going to come out to be positive down here. So just look at the numerator. Negative 8 minus 3, negative. Negative 8 plus 7, negative. Negative times negative, positive. Between negative 7 and negative 2, we could test with negative 6. Negative, positive, so that's going to be negative. Between negative 2 and 3, we could test with 0. Negative, positive, that's negative. And then bigger than 3, positive, positive. Okay, so relative max where? Very good. F of negative 7, which is negative 20. And then relative min where? F of 3, excellent, which is 0. Nothing at f of negative 2. F of negative 2 does not exist. It's undefined. There's a vertical asymptote there. Besides the fact it's decreasing on both sides. Okay? Good. So now let's look at an application, because this is business calculus, of course. So suppose the cost function for a product is as follows. C of Q equals 80 plus 18Q. That's cost. And then the price function is P equals 70 minus 2Q. So part A, find the number Q of units that produces the maximum profit. And then B, we want the price per unit that produces the maximum profit. And then part C, while we're at it, tell us what that max profit is. Okay, so let's remind ourselves how we find profit. Profit is equal to your revenue, all the money that comes in, minus your costs. And then how do we compute revenue, all the money that comes in? Well, it's the price times quantity, number of items that are actually sold. P times Q. Little p, okay? So let's write out our revenue function. It's a function of Q. They gave me the price, our demand equation, 70 minus 2Q, times the quantity, that's just Q. So this comes out to 70Q minus 2Q squared. There's revenue. Then the cost function is right here. 80 plus 18Q. So profit we're going to write with capital P. So P of Q is R of Q minus C of Q. I have R of Q. It's 70Q minus 2Q squared minus C of Q is up there in green, 80 plus 18Q. So here's my profit function, capital P of Q. If we combine like terms, what are we going to have? Negative 2Q squared, 70Q minus 18Q plus 52Q, and then minus 80. Boom. Here's my profit function. Now they want me to go ahead and figure out what is the max profit, where does it happen, etc., etc. Before we do that though, let's identify the domain. Now, this is a polynomial, so you might say all real numbers, but it doesn't make sense for Q to be negative. You're not going to make a negative quantity of items. So at the smallest, Q is 0. You make absolutely nothing. So the domain goes from 0 to positive infinity. Let's just keep that in mind. Okay, so we want to maximize. We want to see where this function, this profit function, has a max. So in order to do that, we need the critical numbers, and we'll do our first derivative test. To get critical numbers, I take the derivative. So it's going to be negative 4Q plus 52. And then I want to know, where does the derivative equal 0 and where does the derivative not exist? It equals 0 if negative 4Q plus 52 is 0. So that happens when Q is 13. And then this derivative, it exists everywhere, so there aren't any critical values from the second condition. Okay, so now let's go ahead and apply our first derivative test. Notice I'm making a number line with an arrow only on one side because the domain is restricted from 0 to infinity. This is P prime, here's 13. So plug in something between 0 and 13 into the derivative right here. How about 1? Negative 4 times 1 plus 52, that's positive. P prime is positive, that means profit function is increasing. Pick something bigger than 13. How about 20? Negative 4 times 20 plus 52, negative 80 plus 52, that's negative. That tells me profit is decreasing there. So yes, indeed, I can see Q equaling 13 yields the relative max. So let's go answer all the parts A through C. So A, find the number Q of units that produces maximum profit. Okay, so Q equals 13 units. That indeed gave us the max. B, find the price per unit. Where's my price function? It's right here. Lowercase p is 70 minus 2Q. You know, sometimes I have students who write all in caps and it's problematic. So in math class, you can't do it. My husband's an architect, though. He writes in all caps. So, you know, depending on your field, it may be okay. It may not be. But right now, no. 70 minus 2Q, 70 minus 26. The price is $44. Did they say dollars? No, we could be in euros. Who knows? I'll just put a dollar sign, though. And then part C, find the actual maximum profit, capital P. So you're going to plug that in to the profit function that we have over there. So part C, capital P of 13 is negative 2 times 13 squared plus 52 times 13 minus 80, and this comes out to $258. So what does that tell you? Don't make more than 13 units because it won't be profitable. The price drops more than the money that's coming in. Isn't that interesting? Okay, so that concludes the lesson. Hope you enjoyed it thoroughly. Don't forget to give the video a thumbs up and subscribe if you haven't already. And then stay tuned, more business calculus lectures coming your way. Also, don't forget to follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later, guys. Bye.